The gentleman on this slide is Howard Levene. His test for equality of variances is the subject of this clip. Here you see Pascal Oosterik, student of Wageningen University. He tells enthusiastically about a practical in a forest near Wageningen. In this clip, I will use data collected by Pascal and other students of forest and nature conservation to illustrate the Levene's test. In the black and white figure, you see tall trees with large crowns and small trees with small crowns. The trees with the large crowns are called dominant or codominant. In our example, these trees are in group 2. The trees with the small crowns are called intermediate or suppressed. These are in group 1. Our research hypothesis is that growth of dominant trees is larger than growth of intermediate or suppressed trees over a 2-year period. We will use a 2-independent sample t-test. There are 2 versions of this test. The classic test, assume equal variances, and an approximate test for unequal variances. How can we decide what version to use? A side-by-side box plot gives an impression of the spread in growth of trees in the 2 groups. As you see, the spread in growth among trees in group 1 seems smaller than in group 2. Possibly suppressed and intermediate trees are not able to grow that fast. Dominant trees can grow fast, but some don't, for instance when they are diseased. The descriptive statistics show that the sample variance in group 2 is 4 times as large as in group 1. So, the box plot and descriptives suggest that the equal variance assumption may not be tenable. However, this marked difference in spread could be due to chance. Therefore, we are going to conduct a formal test. We test the null hypothesis that population variances are equal against the alternative hypothesis that they are different. We will use a significance level alpha of 0.05. In SPSS, we simply ask for a 2-independent sample t-test and we will get the results of Levene's test as well. This is the result for our example. We already had a look at the group statistics, so we can ignore the top table for now. The right part of the second table is the accuracy t-test, and will only be interpreted after we have decided upon variances being equal or not. So we look at this part of the table first, the results of Levene's test for equality of variances. As you can see, the value of a test statistic f and the p-value are reported. We will not discuss the test statistic f or its distribution. We will only look at the p-value in the column sig, where sig is short for significance. The p-value is smaller than 0.05 and hence we reject the null hypothesis of equal population variances. It is shown that the population variances are not equal. So the assumption of equal variances is not tenable. How to proceed with the t-test? We have to use the output given in the second row of the table, where we can find the outcome of test statistic t, approximate degrees of freedom for the t-distribution when the null hypothesis is true, the two-tailed p-value, the mean difference between the groups, and the standard error of this difference. I assume that's obvious what should be done when Levene's test is not significant. Let us have a closer look at the results of the independent sample t-test with equal and with different variances assumed. We look at the test statistics first. On the left we have test statistic t when equal variances are assumed, and on the right t prime when equal variances are not assumed. Note that the prime is just there to indicate that the test statistics are not the same. The numerators of both test statistics are the same. The difference between the sample means y bar 1 minus y bar 2 minus the value of the difference under the null hypothesis d null, which is often 0. However, the standard errors in the denominators differ from each other. When equal variances are assumed, the standard error is calculated with the pooled variance. The sample variances are pooled because they are estimates for the same population variance. When variances are not assumed to be the same, the separate sample variances are used. Only when the sample sizes are equal, the denominators will be the same, because in that case, the mean of the sample variances in the right-hand expression is equal to the pooled variance in the left-hand expression. The distributions of the test statistic when the null hypothesis is true are different. Both follow a t-distribution, but not with the same degrees of freedom. For t, degrees of freedom are equal to sample size n1 plus sample size n2 minus 2 degrees of freedom. For t prime, the number of degrees of freedom is smaller. It follows from an approximation and it is not an integer number. It can be read from the SPSS output. Here you see the SPSS output for the two independent sample t-tests applied on the tree data again. Since the sample sizes are not equal, as you can see in the table group statistics, the estimated standard errors for t and for t prime are different. And hence, the outcomes for t and t prime are different. In the next column, you see the degrees of freedom for the null distribution. For t, it is 138 plus 49 minus 2, which is 185. And for t prime, SPSS gives 164.9. P-values will be different as well. However, in this particular example, outcomes for t and t prime are large, and the p-values are quite small, 0.000 for both. Note that for smaller outcomes of t and t prime, the difference in p-values may be more marked and even may result in different conclusions with respect to the research hypothesis. So, when you have an independent sample t-test situation, do not forget to apply Levene's test for equality of variances first.